Today we're unlocking Rust's most powerful feature, one that eliminates memory leaks and race conditions at compile time. And don't worry, we're going hands-on with code examples so you can see exactly how it works. All right, let's start with the basics. Unlike garbage-collected languages like Python or Java, Rust doesn't have a runtime garbage collector. Instead, Rust enforces strict rules at compile time to make sure memory is used safely. The core of Rust's memory management is the ownership system, which follows 3 golden rules. Each value in Rust has a single owner. When the owner goes out of scope, the value is automatically deallocated. You can borrow data, but only under strict conditions. This might sound complex, but let's jump into code and see it in action. Let's start by seeing how ownership works in Rust. Open up your main.rs file and type this. Here, S1 is a string, which means Rust is storing it on the heap. The variable S1 is the owner of this data. When S1 goes out of scope at the end of main, Rust automatically frees the memory. But here's where things get interesting. What if we try to assign S1 to another variable? Let's do that and see what happens. On assigning S1 to another variable, we get a compile time error. Why? Because ownership was moved from S1 to S2. Rust doesn't allow S1 to be used anymore after the move, so this prevents memory issues. But wait, what if we clone the data instead of moving it? Let's fix our code. Now it works. Clone creates a deep copy of the data on the heap, so both S1 and S2 own separate versions of Hello Rust. This is different from languages like Python or JavaScript, where variables just hold references instead of owning memory directly. Okay, so what if we don't want to move ownership but still need to access the data? This is where borrowing comes in. Instead of transferring ownership, we can lend our data to another variable using references. Let's tweak our code and see how borrowing works. See, no error this time. S2 is borrowing S1, but ownership still belongs to S1. Now, here's where Rust really shines. It enforces a rule called the borrow checker. Rust allows multiple immutable references, but only one mutable reference at a time. Let's try another example. We get another compile time error. Rust won't let us create a mutable reference, R3, while immutable references, R1 and R2, are still in use. Why? Because if multiple parts of the program were modifying the same data at the same time, it could lead to race conditions and crashes. Rust prevents this before it even runs. Alright, so how do we modify a borrowed value? Simple. Just make sure there's only one mutable reference at a time. Watch this. See? Now it works. Since R1 is the only reference to S, Rust allows us to mutate it. Once R1 goes out of scope, we could create another reference if we wanted to. This is one of the hardest parts of Rust, but once you get it, everything else makes sense. Keep experimenting with ownership rules, and it'll become second nature. Now, here's your challenge. Try modifying the code examples we wrote today. See if you can break the borrow checker and understand Rust's error messages. Drop a comment below if you have any questions.